Okay, this is the law of Biot, part two. So we're on part two, and so we finished that last one, and I had this integral, and it got pretty complex, um, in that I have all these constants in front of this integral: mu naught I a over 4 pi, and I'm trying to take the integral of dy over y squared plus a squared to the 3/2 power. And I'm integrating from y equals negative infinity, because our wire goes way down there, all the way to y equals positive infinity. But you know, when you go way down there or way up there, they hardly add anything to the field. They don't, because r is so huge. When you're way down there, the r is so huge that and the theta is so small that you hardly add anything. Well, I'm going to tell you, if you were kind of looking forward to seeing me solve this integral, I'm not going to do that. But if you went to a table of integrals, or if you plugged in this integral into your calculator, it could tell you what the answer to this is. The answer to this turns out just normal integration by substitution doesn't get this done, but maybe a little trigonometric substitution would. And you get this. You get mu naught I over 2 pi a. Ain't that nice how it simplifies to mu naught I over 2 pi a, where a is just the distance that you are if you drew a line from the point that you want to a line that was perpendicular to the wire. That's a. Okay, so there you have it. So it's mu naught I over 2 pi a. Now, next, I want to show you how this gets used with a different situation. Sometimes they have problems with the law of Biot that are much more simple to do than the last one. And so this is a very typical problem in AP Physics or in just introductory physics. Excuse me. So you'll see why it's a lot easier to do. You have a wire that is moving along like this. The current's moving along, and then it goes in this semicircular loop, and then it continues on its way. And they want to know the field right at this point. So the question is, what is B right there? Okay, let's figure out what direction it's going, first of all, the B. Well, it turns out that, you see this part of the wire, it doesn't put any field right here. Nor does this wire. Because if you think about it, if this is your DL, and this is your DR, do you see the angle between DL and DR is 0? And so when you use this equation, I dl sine of theta all over r squared, the angle theta is the angle between dl and r, and so that's going to be 0 degrees, and the sine of 0 degrees is 0. So there is no magnetic field from this part of the wire or this part of the wire. However, this part of the wire there is a magnetic field, but you get a lot of nice cancellations. Okay, for one, take a look. If this is my DL, the DL is going tangential there, and this is my R. Do you see what the angle is between DL and R? It's right. It's a right angle. That's 90 degrees. The whole time, no matter which part you're on, like if you're here or up here, DL and R are always at a right angle. So you can make this sine of, this is really the sine of 90, which is just 1 the whole time. Okay. Another thing about this is that R, this vector R, never changes in size. It's always the same size. And so that you can treat as a constant too. For this path, it's always a constant A. And so let's see what we get when we do this. We get dB is equal to, let's pull out all the constants. Mu naught I is a constant. Sine of theta, I'll just call that 1. And then I got 4 pi, and our r happens to be a, and it's a squared. And then I'm going to sum up all the DLs. But when I add up all the DLs, if that's the only thing in my integral, what are all these DLs when I add them all up? These little distances, DLs. When I get done summing all those DLs, I'm thinking that what you get is the half of the circumference of a circle. So when you sum all those up, what you get is mu naught I all over 4 pi a squared. And then this integral is going to give me pi times a. Not 2 pi a, because this is just a half a circle, so it's just pi times a. So we can cancel out a pi and an a. So the field, oh, I'm sorry, I made a mistake here. When you integrate this, you get rid of, when you get the whole b. It's not just, this is just for one little b. But once you integrate it, then this becomes the total b. And so the total b is going to be equal to mu naught I all over 4a. How nice. How nice is that? It's mu naught I over 4a. Okay. So that's how you use the law of Biot-Savart. There's other things that you can do as well to make a fairly difficult problem become much easier. For instance, what if this went like this? What if instead of doing this, it came in like this? Let me get a white background. So here are 2 wires. Those are the 2 wires coming in, and then it circles around like this, and then it goes out that way. Well, you see this DL? It's always at a right angle to R. And so it's pretty much the same as the last problem. You can pull everything out of your integral. And when you sum up all these DLs, it turns into 2 pi a. So that's the only difference. Okay? So that's how you can apply the law of Biot-Savart in some simple situations. Thanks. Bye.